In the realm of compressive sensing, a novel approach has been proposed to reconstruct images from undersampled measurements. This new framework, known as MOSAIC, masked optimization with selective attention for image reconstruction, leverages the structure of an orthogonal sampling basis and dispenses with the need for deep unrolling. The proposed model is an end-to-end trainable deep reconstruction model that is not restricted to a specific learned sampling process. The introduction of this research highlights the advancements in compressive sensing, which allows for accurate signal recovery from highly undersampled measurements. Traditional CS solvers employ iterative algorithms such as projected gradient methods to solve an ill-post inverse problem. However, these methods have been replaced by deep learning models that achieve faster inference and higher accuracy. These models, including ISTA-Net++ and TransCS, use CS recovery algorithms as inspiration for their model architecture, incorporating techniques like CNNs and transformers to model the parametrized projection and gradient update step. The proposed MOSAIC model draws inspiration from the concept of a measurement filling problem, similar to that of sentence completion in natural language processing. By employing attention in the measurement space, the model can identify and encode the maximum amount of information from any random set of measurements. This approach is particularly innovative as it does not require the sampling matrix to be learned, thus making it more flexible and adaptable. The related work section discusses various deep CS reconstruction models, including black box CNN models and deep unrolling models like ISTA-Net++ and TransCS. These models have shown promising results in achieving state-of-the-art reconstruction accuracy on standard image datasets. However, they are limited by their reliance on specific learned sampling matrices and the need for deep unrolling. The MOSAIC model addresses these limitations by introducing a new approach that is both single-shot and non-restrictive. It utilizes an attention mechanism to focus on the most salient measurements, enhancing the reconstruction accuracy. The model's performance is validated through a range of experiments, demonstrating its potential as a promising alternative for existing CS reconstruction methods. This research proposes a novel method for compressive sensing of images using a structured sampling scheme and attention-based image reconstruction. The proposed pipeline begins with the selection of a subset of M measurements from the total N measurements, following a uniform distribution to minimize sampling biases. These measurements are then embedded using the structure of the transformation matrix phi, generating high-dimensional representations that can be fed into the subsequent model. Each embedded measurement is further embedded using a learnable embedding and positioned using a positional encoding, resulting in the final embedding. The embedded measurements are treated as an element sequence and fed into a masked encoder, where measurements with indices in SC are considered unmasked, while those with indices in SSC are masked. This process is akin to a masking operation on the sampled measurements. The use of a masked encoder allows for the learning of useful representations in the measured space, facilitating the decomposition of the measurements. The reconstruction process employs a self-attention mechanism, where the masked embeddings are padded with placeholders and transformed to predict the original image. This approach leverages the spectral decomposition of the image, where a one-to-one mapping exists between the choice of measurement basis vectors and the measurement values. By using this structured sampling scheme and attention-based reconstruction, the method addresses challenges in compressive sensing, such as spectral biases and the need for careful design of deep networks. The proposed method also draws parallels with representation learning from transformed domains, highlighting the importance of preserving high-level semantics and low-level statistics in the frequency domain. The paper presents a novel approach to compressive sensing, introducing the MOSAIC model, which leverages transformer architectures and structured sampling matrices for image reconstruction. This method significantly outperforms previous models in terms of both PSNR and SSIM metrics across various compression ratios, without requiring a learned sampling matrix. The model's design is based on an asymmetric encoder-decoder structure, where the encoder operates on measurement latents and the decoder reconstructs the full image in the pixel domain. The use of a predefined, structured sampling matrix as a prior for reconstruction proves advantageous, demonstrating the model's generalizability and robustness to noise. Quantitative results show that MOSAIC consistently produces faithful reconstructions across different compression factors, surpassing models with fixed or learned sampling matrices. It also has fewer learnable parameters compared to similar transformer-based models, such as Trans-CS, while achieving better performance. Moreover, the model exhibits robustness to noise, showing improved performance over previous work even when measurements are corrupted with Gaussian noise. The experiments validate the generalizability of the model and its ability to effectively isolate and reconstruct the underlying image pattern, distinguishing it from random noise. Here is the combined summary. The authors evaluate the robustness of their proposed model, MOSAIC, to noise during inference on the $100 Bahamian dataset. Table 2 presents the results, demonstrating that MOSAIC outperforms existing methods, including ISTA-NET+, CS-NET+, AMP-NET9BM, and Trans-CS, in terms of PSNR and SSIM across various noise levels and compression ratios. Figure 3 illustrates the relationship between model parameters and performance in PSNR, further supporting the robustness of MOSAIC. Additionally, a visual analysis of test reconstructions is provided in Figure 4, showcasing that visual-level discrepancies become obvious only at low compression ratios. For instance, the zebra image from set 14 and the butterfly image from set 11 demonstrate the preservation of high-frequency content by MOSAIC. Figure 5 visualizes the performance of MOSAIC across various compression ratios using images from the Set 11 and Urban 100 datasets. An ablation study is conducted to identify the importance of different modules in the MOSAIC model. Table 3 presents the results, which indicate that the model output shows only a slight variation for most larger configurations of transformer block counts. The 16-layer configuration is selected as the baseline model. Furthermore, the effectiveness of the proposed embedding scheme is evaluated, and the results demonstrate that embedding the sampling matrix information into the measurement improves reconstruction performance. The authors conclude that MOSAIC achieves state-of-the-art performance in compressive sensing reconstruction tasks, attributed to its ability to preserve high-frequency content and its robustness to noise during inference. The ablation study provides insights into the importance of different modules in the MOSAIC model, guiding future research directions. The research paper discusses MOSAIC, a masked encoding-based inverse solver for compressive sensing (CS). It reformulates the CS inverse problem as a learnable measurement unmasking problem in a latent representation. The proposed embedding, along with masked optimization, allows efficient reconstructions. MOSAIC achieves state-of-the-art performance across a wide range of compression ratios on various benchmarks. The strong inductive bias given by explicitly using the structure of the measurement vectors accounts for such improvements. The paper also explores the choice of sampling basis, adaptive selection of measurement vectors, limitations, and future directions. It concludes that MOSAIC demonstrates the possibility of learning a general inverse mapping from a random selection of samples for CS reconstruction through a given basis. Here is a combined summary of pages 11 and 12. The authors present a comprehensive evaluation of their proposed MOSAIC model for compressed sensing (CS) reconstruction. Table 4 compares the PSNR, SSIM metrics of MOSAIC with other state-of-the-art models on 3 benchmark datasets, Set 5, Set 11, and $100 Bahamian, at various sampling ratios. MOSAIC demonstrates competitive performance, with a mean PSNR of 47.21 and SSIM of 0.996 on the Set 5 dataset at a sampling ratio of 0.5. Table 5 shows the results of MOSAIC trained on a sampling ratio of 0.125 and inferred on samples with a ratio of 0.1. The results are comparable to the recent best models, with MOSAIC achieving a PSNR of 30.43 and SSIM of 0.905 on the Set 11 dataset. The authors also evaluate the robustness of MOSAIC to noise during inference on the $100 Bahamian dataset. Tables 6 and 7 present the results, showing the reduction in accuracy as the noise level increases. The results indicate that MOSAIC is resilient to low noise levels but less robust at higher noise levels. The authors further provide qualitative results, comparing MOSAIC with other models at various compression ratios. They observe better sharpness and reconstruction of fine details in their method, particularly at lower compression ratios. Additionally, they visualize reconstructions of corrupted inputs, demonstrating MOSAIC's robustness to noise at lower levels but decreased performance at higher noise levels. Overall, the results demonstrate the competitiveness of MOSAIC in CS reconstruction and its ability to generalize to different sampling ratios and datasets. However, the authors acknowledge the need for future work to improve noise robustness, potentially by incorporating noise statistics into the MOSAIC architecture. This research paper presents a comparative analysis of the proposed model, MOSAIC, with other existing models in the field of image super-resolution. The primary focus is on assessing the visual differences between these models under various settings, specifically varying the parameter gamma. Figures 7 and 8 showcase the comparison between MOSAIC and other models for gamma equals 0.1 and gamma equals 0.25, respectively. These figures demonstrate that as the value of gamma increases, the visual differences between the models become less pronounced, indicating a higher level of similarity to the ground truth images. In both cases, the ground truth images are sourced from the Set 14 and Set 11 datasets. Figure 9 continues this trend, illustrating the negligible visual differences between the models when gamma equals 0.5. This further supports the notion that the proposed model performs well in terms of visual quality and fidelity, especially as the parameter value increases. Figure 10 introduces a 3-channel visualization for gamma equals 0.1, providing a more detailed comparison between the models. This visualization highlights the differences in color and texture across the models, with the ground truth images sourced from the Set 5 and Set 14 datasets. The paper's methodology involves a systematic evaluation of the models using different values of gamma, which is a critical parameter in the super-resolution process. By varying this parameter, the authors can assess the robustness and adaptability of the proposed model, as well as its ability to maintain high-quality image reconstruction under different conditions. The results presented in these figures suggest that the MOSAIC model outperforms or matches the performance of other models in terms of visual quality and fidelity, particularly as the value of gamma increases. This indicates that the proposed model is well suited for a range of super-resolution tasks and can effectively handle varying levels of detail and complexity in the input images. In conclusion, this research paper provides a comprehensive comparison of the MOSAIC model with other state-of-the-art models in the context of image super-resolution. The findings presented in these figures support the efficacy of the proposed model, highlighting its potential for widespread application in various image processing tasks. The paper discusses the reconstruction models for Gaussian noise-corrupted images, focusing on the choice of sampling matrices. It highlights the use of the Walsh-Hadamard matrix phi equals h, 1, minus 1, for MOSAIC, which offers better learning compared to the non-orthogonal Hadamard matrix h, 1, 0. The relation between sampled measurements from both matrices is detailed, suggesting a practical implementation with a sampling scheme employing h, 1, 0. The parameter count comparison with other models at different compression ratios is also presented, demonstrating MOSAIC's efficiency. The paper references several works on compressed sensing, including iterative hard thresholding, sparse approximations, and uncertainty principles. It concludes by emphasizing the significance of the chosen sampling matrix in achieving better reconstruction results. The paper discusses the concept of image compressed sensing, which is a technique used to reduce the amount of data required for image reconstruction. It highlights the importance of phase information in signals and its potential applications in various fields such as computer vision, speech processing, and compressive sensing. The authors also explore the role of deep learning models in improving image compressed sensing tasks, focusing on the use of autoencoders and transformer-based architectures. The authors emphasize the significance of masked autoencoders as scalable vision learners, leveraging their ability to model complex distributions over images. They also introduce a new framework called Discrete Cosine Transform Network, DCT-net, which integrates the discrete cosine transform into a neural network to enhance image compressed sensing. This approach utilizes the DCT as an alternative to traditional convolutional neural networks, providing better performance and efficiency in certain scenarios. Moreover, the paper reviews several state-of-the-art models for image compressed sensing, including ISTA-net, ADMMCS-net, and GLIP2. These models are based on deep unfolding networks that iteratively refine the reconstructed images through optimization processes. The authors compare these models with their proposed DCT net, demonstrating its competitive performance in various experiments. In addition, the paper touches upon the concept of masked frequency modeling, a self-supervised visual pre-training method that masks certain portions of an image during training to encourage the model to predict the missing regions. This technique has been shown to be effective in improving image recognition tasks and can potentially enhance image compressed sensing by leveraging spatial correlations within images. Finally, the authors discuss the limitations and future directions of their work, emphasizing the need for further research on the theoretical aspects of deep learning-based compressive sensing. They suggest exploring different architectures and loss functions to improve the efficiency and accuracy of image compressed sensing models.